Hey guys, this is Will here, and I'm here to talk about what I made for the first week of how to make almost anything, one of my courses here at MIT. So the goal this week was to make a press fit kit, meaning something that you can make individual pieces out of cardboard and press them together into a three-dimensional shape. A lot of people have made boxes and structures and even furniture out of press fit kits. What I ended up making is a Dna Double Helix, and here is the model I made in Grasshopper and Rhino. Actually, my main goal this week was to learn Grasshopper and Rhino. I've never used it before, and I've typically used SolidWorks in the past to do solid modeling. And I heard a lot about the power to do parametric design and Grasshopper, and I really wanted to try that. The reason why I'm interested in making a Dna Helix is I'm taking another course right now. I'm taking it at Harvard, and it's a course in synthetic biology. We're actually, in this course, we are trying to design DNA nanostructures out of DNA helices, where you're sort of using multiple DNA helices that sort of fold with each other into shapes. And I found in that class, it's pretty challenging for me to really visualize and get a grasp of what DNA actually looks like. So I thought it'd be a really great opportunity for this week's project and how to make a physical representation as well as a software representation of DNA that I could play with and see and understand better. So this is the output of the program. It creates a three-dimensional solid model, as well as all of these sort of planar two-dimensional models that can then be printed out on a laser cutter. So just to, looking at the Dna Double Helix here, there's a few main parts. So right here, these circular circles are the sugars. So I guess stepping back for a second, DNA is composed of two strands, which are these right here, and those strands have two components, sugars and phosphates. And I've modeled sugars as circular in here, and phosphates as these sort of two arms that are joined together. Of course, between the two strands are the nucleotides, which carry the A, T, G's, and C's, which are the information that is carried in DNA. In this model, they are these sort of two pieces that sort of jut out from the sugars, bond to the sugars, and then bond to each other. So cool. So how is this actually generated? Grasshopper is a plugin for Rhino that allows you to create stuff like this. So if you look at the Grasshopper code here, it looks pretty messy. This is my first time ever using Grasshopper. I'm sure there's better ways that I could have done this. I'm sure there's better ways I could have made it look pretty. But basically what Grasshopper does is it's a visual scripting language. So based on a set of inputs, which I have over here on the left, I'm able to create various solids and surfaces. Each of these purple areas is a solid or surface that's created for this. And then actually over here, this huge array of things it's sort of a cylindrical array of each of these pieces that creates the DNA helix. Obviously, if there's a for loop, that would be a great way of doing this, but didn't see that capability. So the interesting thing here, and why Grasshopper is pretty powerful, is the parametric design of it. So you can change these parameters, and it immediately updates what is happening in the solid. So for example, I could make this radius bigger from 25 millimeters to like 50, let's say. So doubling that. And wow, it looks pretty chunky now. May not actually be how I want to create it, but let's say let's make the diameter of the helix much bigger too. And okay, now we're talking. That might be something we might be able to create. So this is a much bigger helix than the one we'd were looking at before. Also, it sort of automatically generates these planar views. You would want to probably space these out for sort of a bigger helix like this. Yeah, so there's other things you can adjust like the chamfer size for when these pieces come together, how big those notches are, the thickness of your material. You can actually even the base pairs per turn. So typically DNA at a low entropy state, I guess, or its most energetically favorable state would be at about 10.5 base pairs per turn, but you can actually model what DNA helices would look like with more base turns or fewer base turns than that if you're so interested. So that's pretty much it from here. This is the solid modeling I did. You can see below the attempts at physically creating this. There's definitely some challenges with making the physical model. These joints here ended up not being very strong, and a lot of load was being borne on them. So in the future, you'd want to design these differently so they could bear more load. The other thing, using a different material, I'm sure would help as well, other than cardboard. Yeah, I guess one thing I learned this week is that if DNA, if it had any more than an arbitrary amount of gravity in its real state in your cells, then it would probably have a different shape than this. So anyway, that's it for me. So I had a really great time, and if you have any questions about the Grasshopper code or how any of this works, you're happy to feel free to look through the code yourself, but also shoot me an email, and I'd be happy to talk about it. Thanks. Bye.